Okay, let's design the beam tensile reinforcement. We already have the dimension of the beam, which is 400 by 800 millimeter rectangular shape. Now, in the beginning of the design, it will prompt you the strength of, in the beginning is strength of concrete, which is right here, data and specification. You can enter your own specified strength. Here I use 35 MPa and 413.7 MPa for FY. Now I'm asked, program is asking the strength of this concrete, this 35 MPa. Type 35. Don't forget to type 0.0 for the float. And then FY is 413.7 MPa. Alright, and then the source of the maximum moment is from the structural analysis. It is the maximum moment result in your calculation. So whenever you have maybe moment distribution or whatever, if you have the maximum moment, then you can go ahead and design the beam, the tensile reinforcement of the beam. So the MU, the maximum moment that I have in the design of my beam is 1171.08, and it's a kilonewton meter maximum moment. Now the RP is the reduction factor for flexure, which is for the beam is 0.09. It's 0.9. I have to type 0.90, and the width of the beam is 400 millimeter. It's a 0.400 meter. The program is asking you the width in meter, alright? So this is the depth of the beam is 800 millimeter. That is 0.8 meter. And now the bar diameter they use, in bar diameter you can try 25 millimeter, 28 or 30, 35 millimeter. Here I use 28 millimeter. I have to convert that in meter, which is 0.028 meter in diameter. And now here we go. Solving for reinforcement ratio P. P1 is the reinforcement, is the balanced reinforcement ratio. Alright, and then you can solve that from this formula here. Alright, there's P here and there's P over here too. This is a bracket, and meaning 1 times multiplied by this thing goes in there, and multiply this again in this part of the equation here. This is minus 0.59 Fy over Fc times the reinforcement ratio. So therefore there are two reinforcement ratio here. It's going to be P square. So therefore you have a quadratic equation because there are two unknowns in there. Alright, so this is the general formula for the design of the beam. In here we're looking for the reinforcement ratio, so we can design, you can use that in the tensile reinforcement for the beam. So, and since because you have the two p's here, two unknowns, we end up in quadratic equation. So by quadratic equation, I program this quadratic equation to solve for P1 and P2. In quadratic equation there are two results, the P1 and the P2. It's in, for algebra is the x1 and x2. You have to use choose the P that has a smaller value, and the P right here in this case is 0.01 0.01357 is more is also 0.0136. This is the reinforcement ratio you're gonna use to design the reinforcement. The area 1 bar is 0.00616 square meter, and the design of reinforcement using the actual lowest P value. The lowest P value is 0.01356 or 57. Now look for number of bars. Number of bars is 0.7, neglect 0.05. So there are 7 pieces of reinforcement bar at 28 millimeter in diameter. This is the bottom bars. Alright, so we have that using design reinforcement using the actual reinforcement ratio by theory using the moment. Okay, now there is another way of designing using formula, the ACI code formula for the balanced reinforcement ratio. The formula is 0.85, and this is another reinforcement ratio for concrete that is more than 25 MPa. The reduction factor is 85. This is a coincidence. It could be 0.75 for column, 0.65, and 0.70, sometimes 0.9. So this is there's 2.85 right here as a result, because I use the concrete strength here of 35 MPa, so therefore that is 85.85 right there. So this is the formula for the balance reinforcement ratio. Alright, Fc prime divided by Fy times, and this is inside the bracket, and then multiply by this equation right here inside the bracket as well. This is 600 divided by the Fy plus 600. Alright, 600, you divide that by this. So now introduction factor for P balance, which is it is 0.85. I only enter one. This is a one click, and then because of its program already, and all I need there is the reinforcement ratio, and it's already a program how to, and the Python will execute that program and give you. See, this is a coincidence that the P here by formula right here, using formula, is also equal to 0.0136. This is seldom happen like this, so that's why using the formula also gives out the same number of reinforcement bar. For 0.5 P max, there are 7 reinforcement bars. For 0.4 P maximum, you have a choice here, right? You have a choice from 0.1 to 0.5 P max as the reinforcement ratio, and then for the 0.3 P maximum, it gives us 4 bars right here, but it's 5. We round it up. This is actually 6, 7, 5, 6, 7, and this is like 3. For 0.2 P max, this is too small, so I usually go with 0.5 P maximum. This is 7 pieces of reinforcement bars, and at the diameter of 28 millimeter in diameter. So it's seldom that this thing happens, that the P in by formula is also equal to the Usually using the moment right here, solve for the P, the beam always 80% failed. It's either under reinforced or over reinforced. The actual that is easy to use is by formula to find the P maximum. Here the P max is 0.0272, and then you can use up to 0.5, from 0.1 up to 0.5 P max. So that's why here this is the P5, this is 0.5 P max. So 0.136, almost the same as the using the maximum moment. So there are two different ways of designing the reinforcement bars. One is by using the maximum moment and solve for the reinforcement ratio, and number two is solve for the reinforcement ratio using ECI code's formula for the reinforcement ratio balance formula, which is this one here. Alright, so the advantage of having the structural design program is you can always change and play around with it, and you can learn more by doing that than doing it in manual calculations. Alright, thanks for watching. Bye.